As the last meeting, we reached to the membrane fouling. We speak mostly about the advantages of the membranes and applications, and we say that the membrane is very good because we work on the membrane science. But membranes have some demerits, and the main demerits is membrane fouling. The process of membrane is easy, and the fabrication and the fabrication of a plant is very simple. We need some cartridge filter, some tubes, some pressure vessels, and some pumps. But the maintain of the membranes is very important and need to good science about the membrane science. Some plants change every 2 years the membranes, and similar plants in another city change 5 years the membranes, because the engineer of the 5 years have a good science about the membrane keeping and cost control of the conditions for reducing of the membrane fouling. Therefore, we must learn about the mechanism of the membrane fouling and try to reduce the fouling agent, named as foulants. Fouling agent that cause to the fouling. Generally, we have 4 types of fouling, 4 types. One is colloidal fouling. That means the fouling agent is colloids and particles. Particle fouling or colloidal fouling. Why say colloidal? Because we can separate particles, big particles, and colloids is very small and charged particles. And in some cases, the cartridge filters cannot good remove the small particles that we say colloids, and therefore we can have a colloidal fouling. Colloidal fouling is important in microfiltration membrane, because in the microfiltration membrane we mostly separate the particles, separate the bacteria and yeast or the turbidity. Therefore, in this case, the colloidal fouling is important in microfiltration and ultrafiltration membranes. No important in reverse osmosis, because we don't allow to reach the colloidal to the RO surface. If reach, RO rapidly will be removed. The second type of the fouling is biofouling. Biofouling, that means the reason for fouling is the bacteria, viruses, and living microorganisms. The third one is organic fouling, that the foulants are organic matters, such as dyes in textile wastewater, natural organic matter, humic acid in seawater and rivers, and proteins in milk filtration, and another. The famous one of the fouling is organic fouling, because we have many types of process that we want to concentrate these organic matters. We have concentrate the milk, whey, proteins, fruit pulps and others, and all of have a organic nature. And the fourth foliage is sedimentation foliage, sediment foliage, precipitate foliage, that's named as a scaling. This type of the foliage is named as a scaling and important in RO, NF, MD, important in desalination process. In this case, we have a sedimentation of saturated components with increasing of the concentration of the salts in the surface on the surface of the membrane, with reaching to the saturation point, the extra salts that cannot be dissolved in the saturated solutions will be precipitate and cause to a new layer on the membrane surface. And these crystals can act as a knife and can destroy the membrane surface, can cut the membrane surface. Therefore, this type of foliage is very dangerous. The colloidal foliage can be removed easily, but the scaling is hard. Excuse me. This is also show another schematic about biofoliage, inorganic, organic, and colloidal. For porous membranes, we have different types of the foliage based on the chemistry and size of the foulant and pore size of the membranes. We have a standard blocking. That means the pores is open in standard, but the molecules, the foulants, attached, absorbed on the surface of the pores and reduce the diameter. But in standard foliage, the pore size reduce and the flux reduce because some of the pollutants can absorb on the pore side. One is the complete blocking. In this case, the pores completely block with the foulants, and we have a cake layer fouling or gel layer fouling that we have an extra layer in the membrane surface. This is an example of the colloidal fouling. These photographs, SCM image, have given from the membrane surface with fouled membrane. And we see that the particles cause to the increasing of the membrane thickness, and we have a new layer, that this new layer can cause to reducing of the membrane flux. This is an image about the organic foliage, and you can see the gel layer on the membrane. Membrane is white, but produce a gel layer. This membrane is used for natural organic matter filtering, and after fouling, give the analyzers for characterization of this layer, and shows that the most of them is alginate from algae. From the seawater, there are algae, produce alginate, and alginate foliage very bad in the case of the calcium. When we have a calcium in the water and alginate, calcium can act as a bridge between the alginate and cause a adhesive, and very, very bad fouling can occur when we have a calcium with humic acid or natural organic matters, and produced a layer as a cement on the membrane surface. Therefore, in the entrance of RO membranes, we must use the TOC lower than this amount, 4 ppm. If we have a higher TOC than 4 ppm, we will have a very bad cleaning in RO and NF surface. This shows the scaling or inorganic fouling. We say what is the mechanism of the scaling. When we have a fresh feed on the membrane surface, with passing of the permeate, the concentration of the salts on the membrane increase, and when close to the saturation point, some nucleus are produced and cause to the more growth of the nucleus, and we have a crystal layer on the membrane surface that's based on the crystal type. The crystal type of calcium sulfate is different from calcium carbonate. And therefore, we can have a different structures on the membrane. You see here, you see the producing of the salts in the entrance of the spiral wound modules, or here. And this growth of these salts, these crystals, completely block the entrance of the modules, and the feed cannot go. And in this case, we have a very high pressure drop. We increase pressure from 20 to 50 atmosphere, and in this case, we need high energy for this matter. Scaling mostly can result from calcium and magnesium, but presence of low amount of heavy metals, especially zinc, especially nickel, manganese, iron, or aluminum. We have a coagulation process in the water treatment. That in coagulation process, we add Fe chloride or alum sulfate as a coagulation agent. And in some case, the possibility of the iron and alumina in the feed is high. And this can cause to the rapid sedimentation of the inorganic layer because the solubility of these salts is lower than. The complex of the calcium and magnesium, for example, with hydroxyl, with sulfate, is low, but the tendency of heavy metals for precipitation is high. We usually have this KSP. We know each component that can be precipitate have a KSP. The lower KSP, the minus KSP, means the rapid sedimentation behavior. We say that the calcium carbonate, in comparison to aluminium, have more solubility. Aluminium hydroxide is very, very low soluble. Therefore, when we have a very low amount of aluminium, our phosphate, our both phosphate, our zinc hydroxide, or when go here, iron, Vu very minus. These components can increase the scaling possibility. Therefore, if we have a low amounts of zinc, low amounts of aluminum, low amounts of lead, it may be, we must first remove from the feed of RO. Therefore, I say one plant work 2 years, another plants work 5 years, because the 5 years one is used good pretreatment. And when we have a good pretreatment, we have a use good anti-escalant, good pH adjustment, we can reduce the possibility of the scaling with controlling of this KSP. All of this KSP related to the pH. All of this KSP is related with change of the pH and temperature also. This KSP can be changed because the acid can be interact with hydroxyl and can cause to the change of KSP. We know that with, for example, calcium wants to complex with phosphate, okay? With increasing of pH, we change phosphate to acidic one. With reducing of pH, this change, for example, to this one. And this one have a low tendency to complex with calcium. And therefore, the KSP is changed. Therefore, with addition of the acid, we can change the hydroxyl carbonate change to bicarbonate. And other sulfate can be changed to the bisulfate and others. Therefore, we have a controlling of the pH for reducing of the inorganic sedimentation. You see a SEM image from this module. This module is destroyed, open, and give a SEM image. Here is membrane. You see, if the thickness of the membrane is 50, we have almost 2 times constant height of the inorganic materials, and you see with different structure. I think that have an earthquake and a building put on the membrane surface, okay? Therefore, this goes to the destroying, and you see these crystals can act as a knife and cut the polymer. Therefore, we must control the conditions of the membrane for reducing of the fouling, and we need to washing and cleaning of the membranes. In dairy industry, we every day wash the membranes with hot water, and every week we with cleaning agent, such as surfactant, such as acid base in dairy. In RO, we usually wash every month the membranes. When I say wash, that we use only water. Our water with air bubbles, no chemicals. When we use cleaning, that means we use cleaning agent. But when we say washing, we use only water with mechanical cleaning, such as bubbles, okay? And usually, every 6 months, clean the RO membranes, NF membranes with cleaning agent that based on the foulant type, use different cleaning agent. For these crystals, that is inorganic compounds, mostly use acid. Acid can dissolve these minerals and remove them. But we know the acidic solution is toxic for polymeric membranes. Therefore, after 5-6 times of cleaning with acid, the membranes will be destroyed. Every 6 months, when we clean 6 times, after 3 years, the membrane should be changed. Therefore, cleaning is also destroy the membranes. We can use EDTA. EDTA is a complex we use in titration for measuring calcium, magnesium, and others. Okay? We use in the shampoo for complex with the calcium and reduce the hardness and cause to that the shampoo, soap have a good foam. EDTA can complex with metals and produce the soluble complex. Therefore, with using of EDTA in cleaning agent, we can rapidly dissolve these ones. And other cleaning that I will discuss in the last slides. In the RO, we have a Langelier index that equal to the actual pH minus saturation pH. Which pH goes to the saturation, and actual pH of water, what is that? And for calculation of the saturation pH, we have this equation that shows the most components that cause this layer in water, in river water, in well water, is the calcium and bicarbonate. Therefore, we can use of this equation, we can calculate the saturation pH with having of the calcium concentration and bicarbonate concentration that we easily obtain with titration with EDTA and titration with acid. Okay? If the Langelier index is bigger than 0, tend to participate. If the lower than 0, tend to dissolve. Okay? Bigger than 0. We calculate the saturation pH is 6. Our river pH, water pH is 6.5. Therefore, it's bigger than 0, and this goes to the precipitation. Therefore, we add acid to the feed and increase pH to lower than 6. We go to the 5.5. Okay? Why we do not use, for example, 4 pH 4? We know when we we reduce the pH and reach to the force 3, the possibility of this formation will be reduced. But we do not reduce the pH because causing the corrosion, pH, within reducing the pH, the corrosion will be increased in the pump. And also the acid can be destroyed the membranes, polymers. Therefore, only we very low amount reduce to decrease the sedimentation possibility. I discussed. Scaling layer can be different from one water to another water because the chemistry of water can be different and also maybe another organic fouling, microorganism fouling, biofouling together. Therefore, for comparing with that one membrane surface for UCLA wastewater is different from Montana State University. This is I think this is have a organic fouling together with inorganic, but here we have only inorganic fouling. We see good crystals, but in this case we see some polymeric change, maybe from alginate, lignin, and other natural organic matter. Therefore, because based on the chemistry and water source, our routes, our control can be changed. Therefore, from one plant to another plant, the management of the system can be different, and the engineer can be find the reason problems for fouling and try to resolve them. For reducing of the scaling, after pH adjustment, we can use some matters, some materials that reduce the scaling possibility. The famous one is a phosphonate families. They are different type of this compound that we use. This is a phosphonate families. Or can be used dendrimers, can use polyanions as a polyelectrolyte and others. For example, in the similar wastewater, use similar membrane, one no inhibitor, no anti-escalant, and another only used 5 ppm of phosphate inhibitor in the feed. The scaling agent is used in very low concentration, 1 ppm, 2 ppm, 5 ppm, 10 ppm, not more than 10, okay? With addition of very low amount of this anti-escalant and testing for 1 week, 1 month, they are give this SCM image on the membrane surface and see that the anti-escalant reduced the formation of the crystals. Usually we have 2 mechanisms. We have many mechanisms. Change with the type of the anti-escalant. But we have 2 main mechanisms. One mechanism is the change of KSP. We see that previous slide in this. We have a KSP for any of this sedimentation. When we add a second ligand, we have a metal and sulfate is ligand, okay? Our complexing agent. When we have a new ligand, such as phosphonate, calcium wants to react with phosphonate instead of the sulfate. Therefore, there is an interface. There is a combat between calciums for reaction with phosphonate, not want to reaction with carbonate or sulfate. And phosphonate calcium complex is soluble, not insoluble. If calcium react with carbonate, will be precipitate. If react with the phosphonate, don't precipitate. Therefore, one mechanism is the change of KSP and cause to the soluble complex. The second mechanism is that such as these polyanions, polymers, dendrimers, can connect to these crystals where are alone. You see that after producing of these crystals, all connected together and produce a bigger particles or produce a layer on the membrane surface. In this case, most in polymers, the polymer connect to the produced crystals and do not allow to more growth. After nucleation, the crystal began to grow during the time. But these polymers connect to the small particles and do not allow to growth. And when do not growth, the cross flow velocity of the fluid after a certain time can this pull and exit from the RO modules. Therefore, the attachment of the crystal can be reduced with some polymeric anti-escalant, and there are many mechanisms for that. The temperature of the feed can be influenced. There are many parameters can influence. In this study, shows that when the feed concentration is 5 centigrade, we have a less gypsomic scaling. And when the temperature increased, we have an enhanced gypsomic scaling. That show, in this case, the reducing of temperature can be good. Therefore, the growth of the crystals, the reaction between calcium carbonate, calcium sulfate, is a chemical reaction and have thermodynamic and kinetic parameters. Therefore, with change of temperature, the growth rate can be changed. In this case, we see that the increasing of temperature is bad for membrane from fouling view. But we know with increasing of temperature, the flux can be increased. Okay? We have a two trade-off. Increased temperature is good for flux, but bad for gypsum scaling. The biofouling is the bad fouling because we know the bacteria and the microorganisms had very rapid growth. During 1 day can be 3 times increase the concentration. Therefore, if we have a microbe or microorganism on the membrane surface, it can be rapidly grow and prepare some big colonies. This is shown that when the microorganism can reach to the RO membrane surface due to the bad performance of sand filter, cartridge filters, during maybe 1 month, the membranes completely destroy, and you see the color of the membrane change from white to dark brown. Therefore, the biofouling is very bad fouling and can rapid growth. We say in previous lectures that for increasing of recovery, we usually have a 5 or 6 or 4 modules inside of the pressure vessels. We have a long pressure vessels. We put 5 modules. Each module have 1 meter, and therefore this pressure vessel have usually 6 meters, because between each modules we have a free space of about 10 centimeters. In this slide, we say that the fouling is related to location of the modules also. When we have the feed entrance here, from left, feed entrance, and from the right, the concentrate exists, okay? And we have 6 modules. In the first module, we have a organic fouling mostly. If the feed have an organic matter, the most foulants, organic foulants, can be attached to the membrane surface in the first module. And when the module can absorb the foulant, organic foulant, the concentration is reduced. And in the last module, we have a very low organic foulants because adsorbed, and therefore this module have a very low organic foulant because mostly adsorbed in the first one. Reverse, in this case, we have a desalination process. In this case, I write here, for example, our feed have a (3,000 ppm desalination. Every module have a 15% recovery. That means from this ppm, and for example, we have a 100-liter solution. In this case, if its membrane act as a 15% recovery, 15% in 6 modules, we will have 90% recovery. That means here we have 10-liter concentrate, and as a permeate out, we will have 90 liters, okay? When we have a 90% recovery, that means 90% of feed will recover. That means here, if we have a 100 liters of feed, 90 liters will be permeate, and 10 liters will be concentrate. The concentration of the salt in the feed is 3,000 ppm. And we assume that we have a 100% complete rejection. Usually 99, we assume complete. That means all of the salts will go to the 10 liters. Therefore, in this case, we will have ppm salt, okay? The permeate is pure, distilled water, no salt. All of salts from 100 liters go to the concentrated solution. Therefore, concentration will be increased from 3,000 to 30,000. Therefore, here we have a very possibility to saturation. 10 times we have a thicker solution. Therefore, in the last modules, we will have a possibility of scaling because with going to the right, the concentration of the salt increases, and in the last one, we will have a very bad scaling concentration. Therefore, the fouling is related to the location, and in industry, in annual repairment, usually change the location of these modules. Give this one, for example, use as a tool. Change the location of the membranes for long life. The main reason for fouling began start from the concentration process. As we know, the concentration of the solutes, the molecules, from the bulk to the concentration polarization layer is different. As yesterday, Dr. Raka have some solution problems for you. In the first problem, said that the concentration of the molecules 25 times higher than the bulk in the first, okay? The concentration in the surface 25 more than the bulk, and this means in the previous slide, we say that the concentration of the feed is 3,000 ppm. This concentration is in the bulk. We measure the bulk, not can measure the surface. Therefore, we have actually the concentration of the salt in the membrane surface may be 6,000, 7,000. Okay? Therefore, this concentration polarization, because increase the concentration of pollutants on the surface, cause the fouling. Therefore, the styling is very important in the membrane surface. And we try to have a turbulence fluid regime on the membrane surface. We must have a Reynolds bigger than how amount for turbulence? This number. We must, the Reynolds number more than usually 3,000 on the membrane surface, and the feed speed is very important. Feed speed is very important in the spiral wound, and when we want to buy a module, one of the parameters in the brochure of the membranes is the feed speed entrance. Every higher feed speed, we have a big Reynolds number. We have the Reynolds number, rho, v, d, and mu. And this is the velocity speed. Higher velocity is good for reducing of the concentration, polarization. But higher velocity, that means higher energy, higher pressure. And this causes the deformation of the module. When we have a rapid growth, we have maybe our configuration destroyed. Therefore, in the brochure, in the catalog, say maximum feed speed. And this module should be test maximum feed speed. We want to increase the speed, but maybe the module can be degraded. I go this one. There are different resistance in the membranes that we can calculate them with filtration of the proteins that I discussed yesterday. We test of pure water, foulant, and second water. We have a different type of the resistance. First one is the membrane intrinsic resistance. When we have a pure water flux, we know that the big pores in the membranes is meaning the low resistance. When we reduce the pore size, the flux reduces. That means the resistance increases, okay? Therefore, we have an intrinsic resistance that related to the membrane chemistry and membrane pore size. We have an adsorption resistance, that's standard resistance, that this resistance can be reduced the pore size. We have a gel resistance or cake resistance. We have a concentration polarization resistance, that's difference in concentration. We have a pore blocking resistance, that means completely or mostly blocked with the pores. Based on the flux, we can calculate them that have equations, and this is the routine method. Yesterday I discussed that we can obtain flux recovery ratio with measuring second flux to first flux, reversible fouling and irreversible fouling, that based on the BSA flux, we can obtain these ones. In this slide, I try to define the fouling. For reducing of the fouling, we have three general techniques. One is pretreatment of feed. We can identify, characterize the fouling agent, fouling reason, and remove it or reduce it. Okay? This is the best method that we can control the fouling agent. For example, using sand filters, carbon filters, different culprit filter for removal of a particle and colloids. Using carbon filters for adsorb heavy metals and organic substance. Low concentration chlorination to prevent microorganism growth. We have a 1 ppm chlorine dosing in the feed water of RO. This chlorine as a disinfect do not permit the growth of microorganisms, but I said before that this chlorine can cause to the degradation of membrane in RO, and one of the research is the increasing chlorine resistance of RO membranes. Okay? Polyimide can be destroyed with chlorine. pH adjustment to reduce the possibility, and use of anti-escalant. Therefore, the better one is the pretreatment. We control the conditions of sedimentation. The second one is the membrane modification. We can increase the membrane resistance to fouling. For example, when we have antibacterial membranes, the microorganism cannot be gross, because when come to the membrane surface, will be deactive. Or we can control the pore size. Pore size is very important. When we have a uniform isopore size or narrow pore size, the fouling is very lower than when we have a wide pore size. That means one big, one small. Or we can change the polymer, membrane chemistry. With change of the membrane chemistry, we can reduce the attachment of the organic foulant. With increasing of hydrophilicity, the most of organic matter attachment reduce. Because we increase hydrophilicity, and hydrophobic materials cannot attachment, and there are many. And the bad method that we do not act this way, this is washing and cleaning. When our membrane is full, with washing and cleaning, we can recover them. So this is the Gauss parameter, and I discussed them and some examples in the another slide. For pre-treatment of the feed solution, heat treatment, for example. With increasing of a heat of feed in dairy industry, we can reduce the membrane fouling. Fat of milk in the cold temperature rapidly causing of the fouling. But with increasing of temperature, the oil and fat fouling can be reduced. pH adjustment, anti-escalant, chlorination, and others. Membrane properties, I say that we can increase the hydrophilicity of membrane or control the pore size. Module and process condition, I discussed with a turbulence promoter, we can increase the mixing on the surface and reduce the concentration polarization. For turbulency, we usually two methods. One, increase of the speed, that we say we have a limitation, max speed. The second, using of baffles. Baffle or promoters. Promoters, when we use feed spacer, in the module I speak, between membranes we use feed spacer for passing of the feed. The configuration of this feed spacer is very important and close to the turbulence. We can have a mesh-like feed spacer, okay? This is the structure of feed spacer, as you see in the module presentation. This is this structure that between two membranes, we can produce this feed spacer such as this one. With change of this angle, the turbulence can be changed, okay? Therefore, the design of the module can be very important in membrane fouling. And if our membrane is fouled, we have a hydraulic cleaning, that means washing only with water. Mechanical cleaning, that we use ultrasonic. We use bubbles for cleaning. Chemical cleanings are chemical, we use chemicals such as acid-base surfactant. Electrical cleaning, in some cases, we have an electrical field outside of the pressure vessel, and induction of the electrical field to the cations and anions reduce the fouling. This is electrical fouling. As a membrane modification, as a second, there are many methods for improving the anti-fouling properties of the membrane. One method, improve hydrophilicity for MF, UF, NF, RO membranes, okay? In this case, one famous method is grafting of some hydrophilic monomers, macromolecules, or polymers on the membrane surface and producing brush membranes. Brush membranes. As you see, it is similar to meswak. Huh? You say meswak, toothbrush. This is similar to the toothbrush, and this chain, this brush, do not permit molecules want to attach the main polymer. But this brush do not permit, and this is also have a movement, and the movement of the feet velocity can separate the attached molecules from here and reduce the attachment of the pholons to the membrane surface. Or we can coating. We know coating is the physical attachment, but grafting is mechanical attachment. If we can prepare this layer with a graft, is better than the coat because the stability is higher. Or we can blend the different hydrophilic nanoparticles and polymers or macromolecules to modify the hydrophilicity of the membrane during the membrane fabrication. In this slide, show some pretreatment method for reducing inorganic fouling. As we said, we can use the anti-escalant. We can remove the calcium, magnesium as a softening agent. We can use acidification for decrease the plasticity, or we can use the thermal water softening, such as distillation, for reducing of the software. For organic fouling reduction, we must remove the organic agent. That most used process is coagulation with addition of aluminum and iron salts to water and use of calcium hydroxide, some precipitation produced and adsorb the organic matter and remove from the water. We can produce the antibacterial membranes with addition of the antibacterial agent. For example, silver-based nanomaterials. We know the silver have antibacterial properties. Zinc oxide is the famous. Graphene oxide, boron nitride, or we have antibacterial polymers also. We can mix with antibacterial polymers. And when we have an antibacterial agent, we see this is the live bacteria, and this is the destroyed bacteria. When we have an antibacterial agent, the bacteria can be dead, and the cell membrane of bacteria can be destroyed. Or in this example, when we have a knit PVC, Bayer PVC, that have not antibacterial agent, we see the growth of the microorganisms, and with addition of low amount of zinc oxide to the PVC, the surface is very clean. And this is show that we can produce the antibacterial membranes. For increasing of the hydrophilicity, we can also modify the main polymer. When we have a polysulfone, with addition of the functional groups, such as sulfonic, such as carboxylic, such as hydroxyl groups, we can increase the membrane permeability and antifouling properties. For this production of these groups, there are different methods. One is the plasma treatment. Can oxygen plasma can produce the radicals and cause to the hydrophilic surface on the membrane surface. Or with production of copolymers produced from two different polymers, with combination of the hydrophilic polymer with hydrophobic one, we can increase the hydrophilicity of the membrane And when in this research, when 10% ethylene glycol is inserted to the polysulfone structure, we see that the permeate is very, very increased. We can graft the many functional groups to the membrane surface. We have a UV-induced or plasma-induced grafting. For grafting, we must first active sites. For producing active sites, we can use UV irradiation, plasma irradiation, or gamma and other high energies. Blending of additives, hydrophilic additives, can locate on the surface of membrane and inside of the membranes and cause to the decreasing of the fouling attachment. For cleaning, we say we have a physical cleaning that use water as a hydraulic cleaning, or mechanical cleaning with use of ultrasonic and bubbling and others. Usually, the physical cleaning is a few minutes in the industry. For cleaning, washing with acid base, we usually 1 hour use. For mechanical and physical cleaning, we use 5 minutes because we want the water can wash the membrane surface. But in the cleaning, we need time for reaction between cleaning agent and fouling. For example, we want to remove the scaling. When we use acid together with EDTA, acid and EDTA should go and react with calcium carbonate, calcium sulfate for dissolving it. And dissolving needs time. Therefore, we usually use 1 hour. We do not use more than 1 hour because more contact causes to the damage of membrane. And rapidly after cleaning, we use the water for removing of the cleaning agent. In the washing of membranes, we have 2 types of washing. One is forward washing, second is reverse washing, or back washing. Forward, reverse, back. It's 3 types, okay? Back wash, that means we insert the permeate from bottom to surface. We usually filter from the surface to the bottom. Backwash, that means we return some of permeate from bottom to surface, and this movement from the permeate side to feed side cause to entrance the molecules and remove this layer, okay? This called is backwash. But we have a forward and reverse washing or flushing. In this case, we only, instead of feed, we use the water from the surface of membrane, okay? In the forward flushing, our direction is similar to the feed. When we have this model, feed come here, and here is concentrate. Okay. In the forward wash, we close the feed value and open the wash value, wash valve. With opening of the wash valve, forward, parallel to the feed is clean. But in the reverse, we have this side. We have used the washing from the concentrate side to feed side. In back, what happened? In the backwash, we used washing from the back side, okay? Forward, reverse, and back flush. This is the back flush. For washing and cleaning, we measure the pressure drop or flux drop. Our flux, for example, is 100. When reached to the 50, we say that our membrane should be clean. And this time maybe 1 day for UF or 6 months for RO. After reaching to this criteria, this critical point, we must wash the membrane. But with washing or cleaning, we usually do not reach to the first flux. And the flux is lower than the initial flux. And after another period, we again wash, and we repeat this process. And after 5-6 times for RO membranes, or 1,000 times for UF membranes, the recovery of the flux is very low, and we must change the membranes. This diagram is for flux, and this diagram is based on the pressure. In industry, we want to produce a product, and the product capacity should be constant, okay? We want every day have 100 liters of product. But when flux is reduced, our product will be low. For this purpose, with decreasing of the flux for keeping of the product amount in 100 liters, increase the pressure. Our applied pressure should be 2 atmospheres, but because our membrane is full and the product is lower, therefore increase the pH to reach 100. Tomorrow, more increase the pressure. And after 6 months, the pressure reached from 2 atmospheres to 6 atmospheres for keeping the amount of products. Therefore, in industry, most use this method for finding the backflushing time. Therefore, with keeping of the pressure, with increasing of the pressure, we have a constant productivity. I go from. As a mechanical washing, we can have a bubble flow from the water, and this bubble can increase the membrane cleaning, that's named as air flushing. We can use ultrasound. Ultrasonic can produce very small bubbles and can cause the attachment of the pollutants from the membrane surface. And finally, if our fouling is very bad, we have to use the cleaning agent. We have 2 types of the cleaning: clean in place and clean out of place. Most of cleaning is cleaning in place. That means we do not exit the module from pressure vessel. only instead of feed, we insert the cleaning agent. Or in the backwash, we insert from the permeate side. Therefore, in cleaning place, that's mainly CIP, we use the cleaning agent in that place, but in very bad fouling, that in many cases we use the cleaning in place, but the flux is not come back. Therefore, in these special conditions, get out the modules and go to the lab, and in lab with different chemicals, test for recover the models. I go on this table. So for summary of the cleaning agent based of the fouling material. Okay, this table is important. When we have a biological fouling and natural organic matter or synthetic polymers, polyelectrolyte, the best chemical agent is sodium hypochlorite. Sodium hypochlorite can produce from reaction of NaOH with chloride. This is a strong oxidizing agent and can oxidize the organic matters. All of these three, biological, NOM, and synthetic polymers, are organic matter. And organic matter can be good oxide with hypochlorite. Or we can use another oxidant. Another oxidant is hydrogen peroxide. Hydrogen peroxide is expensive, but hypochlorite is cheaper one. And for natural organic matter, we can use NaOH. NaOH can react with organic matters and produce soap. Washing soap produced from fatty acid and NaOH. Okay? We use the soaps for our washing, usually prepared from fatty acid plus NaOH. We can use the ship fatty and NaOH, and when we're boiling the ship fat with NaOH, we can produce the soap. Sabun, you say sabun? In Iran, we also say sabun. This is the reaction of the NaOH with NaOM. NaOM, most of this similar. The structure have this fatty acid. Therefore, when we add NaOH, react with NaOM and produce sabun, and sabun can be easily washed from the membrane surface. For inorganic deposit, inorganic scaling, we use acid. Acid is better. Citric acid, sulfuric acid, or chloric acid. Acids can dissolve the inorganic materials and remove it. Or we can use the complexing agent for removal of the metals or inorganic. For removal of the manganese and iron that is high in the well water, the sodium bisulfite as a reductant agent is good. Hydrogen peroxide and hypochlorite is oxidant. SPS is reductant. With reducing of the iron, we can be removed from the membrane surface. This table is good for selecting of a good cleaning agent. The parameters that affect the cleaning, one, the chemistry of the cleaning agent that we discuss in this table, but the cleaning time is important. Sometimes 30 minutes, 1 hour, 2 hours, based on the chemicals. Temperature is important. We can increase the temperature of the cleaning agent and increase the reaction velocity. Our concentration of the cleaning agent is important. In some cases, we use the acid with pH 1, in sometimes pH 2. And with change of the pH, that means the concentration change. Our concentration of EDTA is important. No need for that. Thank you. If I have any question, what's about it? If any question about the cleaning, fouling.
So what is sponge cleaning?
What it is?
Sponge in mechanical cleaning.
Sponge? Ball?
Sponge
Ball, yes. It is most used for the some hollow fiber membranes and plate and frame membranes. The use of the sponge ball, okay? Sponge ball.
Sponge.
Yes. We cannot use sponge ball in the module of the spiral wound because cannot entrance to the membrane, but in the plate and frame, we can use them. In some hollow fiber, we can use.
What is the mechanism, how it works?
I do not understand your question.
What is the mechanism, how it works?
Mechanism of sponge ball.
Cleaning.
Sponge ball cleaning. Mechanical.
Mechanical.
Yes. Such as the washing of the dishes. We have a sponge that come and mechanical removal of them. Question?
So any other question from the participants? Yeah? So please feel free to ask. Because, yes.
One general question, sir. Sir, what should be an ideal state of a membrane?
Ideal
State, I mean tensile state.
tensile is ideal tensile. Ideal tensile based on the membrane type is different, but you want amount for
For liquid separation.
liquid
So I mean.
in UF.
Yes.
In commercial membranes, most of commercial membranes produce on non-woven fabric. And non-woven fabric very, very stable, such as this cloth, no tear. But when we have a membrane on glass, this stability can differ from one polymer to another polymer. And for example, for cellulose acetate, we have a very strong membrane. But for biopolymers, we have a very lower. But the best one, we have a test for measuring of the stability of strength of membrane as a tensile. We have a 2 in 5 centimeter samples and give to the lab for testing of them. Have a 2 constant of them and began two stretching of them. Usually, the best one in the tearing point have a 50% in elongation. We have elongation. 50% is good. Because we do not more flexible or more rigid. And the second parameter report, it is the strength of the membrane, and usually 70 megapascal is good. When you check the membrane for polyethyl sulfone, polysulfone, PVDF, the reported good data is 70 megapascal.
Commercial membrane?
Commercial, no, for lab. Because commercial paper is on non-woven fabric, and the strength is more 300 megapascal.
So
In the commercial membrane, usually do not report the strength because the non-woven fabric produce the strength. But in some membranes, such as Nafion, such as gas separation, maybe we have not support. In this case, usually because the membranes are not porous, such as Nafion, Nafion is very strength, and you cannot tear them. Gas separation also is very, in this case, more than 100 megapascal is strength.
Thank you.
So maybe I would like to add one thing here, that whenever I see more porosity of the membrane, we have less mechanical strength.
Yes.
Whenever we go for lesser and lesser porosity, then the membrane becomes strong. If we have highly porous membrane, then the mechanical strength becomes less.
Yes.
But whenever we add the support, then that becomes the dominating part of the strength.
Yes.
here.
Yeah.
So
Therefore,
yes.
the non-woven is very important,
Yes.
and we cannot tear the RO membranes because very, very strength. But the polysulfone can be easily destroyed. But when caught in the fabric produces the stability and strength.
Thank you. Thank you all for joining in this tutorial session. So this was the last tutorial session. So and I would like to thank all of you for participating actively in the discussion and listening very carefully and attending all the lectures and taking notes. I have seen reasonably good enthusiasm among the students, but I hope that as our sessions progress in later courses, we will see even more participations in terms of the discussion and question and answer. So thank you all for joining for the tutorial and the lectures today. That was the last tutorial session for this course. And so I request all of you to please join us for lunch in 312. At 2 p.m. I'm going to publish the questions for the quiz, and so I would request all of you to please submit by 3 p.m. You can use either your own laptop or your own smartphone. That way it would be very good. Okay. Thank you so much, and the certificate distribution we are going to start around 3:30 p.m. Okay. Thank you so much.
Thank you. I also for
Actually, sir's input and sir's experience was huge in this sector. And when I was scheduling this course, I was thinking that I'm allotting so much time for him. He will be tired and he will be angry with me. Why you have given so much time for me to talk? Now, sir was telling that time is short. His knowledge is so much. He has so much to give us. And that's why, so I'm so proud to have him here in today's in this session with his knowledge, and that clearly shows the accuracy he has achieved in his life. So thank you for sharing your immense knowledge with all of us. And so I request all of you to please join us for lunch. Thank you.
Thank you. I suggest to give